So in the previous video, we actually introduced the formal definition of the derivative in terms of a limit, and we kind of introduced it graphically as the slope of the tangent line, or the instantaneous rate of change of the function at a given point. And we talked about the different notations, so we have the most common notation you'll see is this f prime of x notation. We also mentioned Leibniz notation, another very common one where the dy indicates kind of a very small change in y and the dx is a very small change in x. And so together they form a very kind of, you can think of it as the slope of the tangent line, because when you vary x an extremely tiny amount, then the dy tells you kind of how much y changes as a result of that infinitely small change in x. And then we of course talked about the I suppose you could say like the Newton notation, y dot, where the dot indicates the number of derivatives you've taken. This is kind of a notation that we don't really use very often, so I'm just gonna kind of erase it, but you may see it in physics if you do take a calculus-based physics course. And so anyways, what I thought would be an interesting activity is to go ahead and take a look at how we can interpret the derivative graphically at different points. So I drew out this arbitrary function over here. It's a pretty interesting looking function, and I kind of marked a couple of points over here. And what we're going to try to do is we're going to try to compare the derivatives, or just at the very least think about what the derivative might look like at these different points. So what is the slope of the tangent line at these different points? So we're going to actually try to draw that tangent line. Of course, this isn't a very accurate thing because we actually need the equation of the function to do this, but we can still get a general sense of what the tangent line may look like at these points. So let's just go from left to right. So we're going to start off with this point over here. And essentially what we're going to do with this point is we're going to think, what is the slope of the function, the instantaneous slope of the function at this point? So we can go ahead and just map or kind of approximate what the tangent line may look like. It may look something like this, right? It will just intersect the graph at this one point and then never intersect it again. And so we know over here that the slope is going to be positive. So let me say dy dx is going to be greater than 0 over here, because clearly the slope is positive. And so we already have that. We don't necessarily know what the slope is. We can get a sense that it is definitely positive. And then if we take a look over here at this next point, this one is kind of a local maximum. If you remember from your pre-calculus or your algebra 2 classes, this kind of could be like an apex or local apex. And if we were to draw the tangent line, it would look kind of something like this, right? This would be just a straight line. It would be or not necessarily straight, it would be like a horizontal line. And the slope of a horizontal line is going to be 0. So at this point, we would have dy dx equals to 0, because it's not really changing at that instant, because at the maximum, it's not really changing. And later on, we're going to look at what that actually means with the first derivative test. But essentially, at a maximum, it looks like the derivative happens to be 0. And then we can take a look at this next point over here, and it looks like we're now decreasing, right? So the slope looks to be negative. We intersect this one point over here, and so we can say, I'm just going to write f prime is going to be less than 0 over here. We can tell because if we were trying to approximate the graph, or sorry, trying to approximate the tangent line at this given point, it looks like our slope is negative. And then we take a look at this next point over here, and it looks like we're also negative over here, right? It looks like our derivative is also negative. But one thing that we have to note is that the slope over here looks to be a little bit less steep than the slope over here. So if we're to compare it, this one is kind of what we can say is, I want to say more shallow. Yeah, I can say it's less steep maybe. This is less steep as compared to this one over here. So essentially, what we're saying is that now, although the function is decreasing, although the derivative is negative, we know that it's decreasing a little bit less. And that's actually a very interesting thing that we have to keep in mind, is that the slope of the tangent line, whenever it's positive, it indicates that we're increasing. So if dy dx is greater than 0, this implies that we're increasing, that our function is increasing because our slope is positive, right? So our rate of change is positive. It means that our function is changing. The y is changing as x slightly increases. And then if our derivative right over here is less than 0, then it looks like we're decreasing. And I mean, we can even just verify that by looking at this graph. And you can pick any arbitrary graph and this will always hold true. And so, but at certain points, we're going to be decreasing more than at certain other points. So over here, we're decreasing a little bit less, even though we are decreasing. but over here we're decreasing even more is the way you can think. So we're decreasing in both of these cases, but in one of them we're decreasing even more. And then we have another, we have what we would call like a local minimum or a local vertex. And what we can do is we can go ahead and just draw out the tangent line. It looks like we're going to have another vertical tangent line, or sorry, horizontal tangent line. So again, dy dx is equal to 0 in this case, because it looks like at this instant we're at a minimum, so we're not really increasing, not really decreasing. And so what we can say is that whenever dy dx is equal to 0, this right over here tells us that we have kind of a local minimum or a maximum. And so, I mean, this is just looking at it visually, right? We can see we're kind of we're decreasing, but then we start decreasing a little bit less and even less, and then, because our derivative is less and less negative, and then we reach this point over here, and it seems like we aren't really decreasing, we aren't really increasing when we reach the minimum. And then our kind of tangent line, or our function starts increasing, and then we reach this point over here, where we have a very steep slope. That's not correct. It looks something more like this. So here we'll have it's not necessarily vertical, but it is almost vertical, right? Like it's a very steep slope. And so in this case, we would say that f prime is greater than 0. But is f prime greater than 0 is also greater than this point over here? Well, indeed it is, because right over here, we're increasing very quickly. Our derivative is very positive, while over here, although we are increasing in this position over here, we're increasing a little bit less. So here we have a much steeper slope. So here we are a lot steeper. It means that we're increasing much faster because our slope is much more positive. And then we take a look at this point, and then we start decreasing a little bit less. We can draw the tangent line like this if you would like. And we can see right over here that f prime is still going to be greater than 0, but this one is less steep. So we are still increasing. Our function is still increasing, as you can tell, but it's not increasing at fast of a pace as we once were over here. So over here we're increasing very quickly. Here we're still increasing, but we're just increasing a little bit less. And then finally we will reach this last point over here, and this one is another maximum. And once again, we notice that we're going to have a derivative equal to 0. And that's because when we reach this maximum point, again, it's like you can think of it as like the shift. We're shifting from increasing, and then we reach this point over here. We're not really increasing, not really decreasing, because we've reached the maximum, and then we start decreasing again as we go along. And so the point is that the derivative is definitely associated with whether or not the function is increasing, decreasing, or if it's at a minimum or a maximum. And essentially, right over here, what I wanted to do is I just wanted to show you how we can compare the derivative at different points of the graph. So we can tell that for this graph, the derivative is definitely not the same everywhere, right? Because we're not increasing in every place. Our derivative is not positive everywhere, and there are certain positions at which our derivative is more positive than other positions. So for example, if we say right over here that this one is equal to 7, let's say, it means we have a very high slope, while over here, if we say that this one is equal to maybe like 4, because it's still positive, but it's not as positive as 7. And so, of course, these are just arbitrary numbers I'm picking just to kind of illustrate what we may observe. And so the point is that whenever you have the derivative, it definitely just indicates to you how much the function is increasing, how much it's decreasing, if it's increasing or decreasing. It may be at a local minimum or a maximum. And kind of the steepness of the line indicates how positively or how much it's increasing or how quick it's increasing if it's a very steep positive line, while if it's a very steep negative line, then that steepness is going to indicate how quickly it's decreasing. And so that's kind of one of the important aspects of the derivative, or kind of the graphical interpretation of the derivative.